In this problem, we have a test made of the null hypothesis, mu equals 20, versus the alternate hypothesis, mu is greater than 20. And we're told that a sample of size n equals 53 is drawn and x bar is 22, and that we know the population standard deviation is sigma equals 5. So this is very important. This is what tells me what kind of test it is we're doing, because we know that this is about a mean. We know that it has to be either a z-test or a t-test, and since we know sigma, it must be a z-test. Next, I'm going to write down the null and alternate hypotheses. We have them here in the problem, but I'm going to write them off to the side, and that way we have all our information coming down this side here. Next, I'll run the z-test. We know what the sample size is, we know the sample mean, and we have sigma. So when we enter all that information into the z-test in the calculator, then we get the test statistic, which is z equals 2.91. Now, in this problem, we were told that the sample mean was 22, and we're comparing that value with mu equals 20 from the null hypothesis. So the value from the null hypothesis is really the center of our normal distribution, and we know that 22 is somewhere above 20, but we don't know. Is it somewhere like here? Or is it somewhere like here? We don't know until we standardize that value, and that's what the calculator is doing for us when it calculates the test statistic. So in this case, we found out that the test statistic is 2.91. I'm going to take this out. And now I'm comparing z equals 0 to z equals 2.91. And so we can see 2.91 is a lot further into the tail, well, obviously than the center. So it's very far into the tail. And what we have to do is decide, is this value far enough into the tail that we are going to reject the null hypothesis that would say the value is really close to the center. So this is really our 20, this is our 22, and so in this case it seems really clear that that 22 is very far away from the center. But how do we know? And in certain cases it's going to be more difficult to tell. It's going to be a little ambiguous because you might be close to the borderline. So you need a defined borderline to know how far into the tail is far enough to reject the null hypothesis. So that's where we have to look at our critical region. So the form of our critical region, I decide this by looking at the alternate hypothesis, and that said that mu is greater than 20. So this is going to be that z is greater than or equal to something. And this is a right tail test. So we used that when we were computing the test statistic. Now we're going to find the critical values, and we're going to round these to 3 decimal places. So first we're going to use alpha equals 0.05. and find the critical value for that. So in order to do that, what we're talking about when alpha is 0.05, I'm just going to sketch this distribution real quick again. So that means that we have 5% in the tail. And the question is, what is the cutoff there? What is the critical value that cuts off that top 5%? And we can find this by entering inverse norm of 0.95 into the calculator, comma 0, 0, comma 1. And where do I get the 0.95? Because this is a right tail test, and we have 0.05 in the right tail, that means that the rest of this area is 0.95, and that's the area to the left. The inverse norm function always works with the area to the left. So this is what we're going to enter. And what does that turn out to be? Let's see. That would be 1.645. So 1.645 is my critical value if alpha equals 0.05. And then we want to do the same thing for alpha equals 0.1, and the critical value in that case is 1.282. And so for that, I calculated same way, but instead of 0.95, then I'm entering inverse norm of 0.90. And that's what gives me that 1.282. So if my critical value were 1.645, well, that would fall right about here. And that means that anything that falls within this area above 1.645 is going to be in the rejection region. So this is defining the rejection region, and our critical value, our test statistic, 2.91, is in that rejection region. So that was one option for alpha, and then our other option was 1.282. Well, that's even going to be a little closer to the center. And so either way, with either value of alpha, we are rejecting the null hypothesis, because in either case, our test statistic is further into the tail than our critical value. So are we going to reject the null hypothesis? Since the test statistic falls in the critical region, we reject the null hypothesis at the alpha equals 0.05 level. And that's how you do that problem.